Good afternoon, actually, so already afternoon. Good afternoon, everyone. So I'm Rui Jiang from Tsinghua University, Beijing, China, and it's my great opportunity to have this chance to present a recent work of mine titled "Uncover Disease Genes by maximizing information flow in the phenome-interactome network." There's been no knowledge about genes that are associated with human inherited diseases, or just simply say disease genes. It's of great importance to the understanding of such human diseases. Also, such kind of knowledge is also very crucial to the understanding of the prevention, diagnosis, and treatment of human diseases. Example would be in drug discovery, where we would like to find some target proteins and design some small molecules to bind to this protein and use these molecules as drugs. And nevertheless, it still remains a great challenge to find such disease genes. For example, if you look at the ISMB database, we could see that the molecular basis for about 60% of human diseases are completely unknown, making it indispensable to develop effective computational methods to aid the discovery of such kind of disease genes. So for this purpose, a lot of methods have been designed from the viewpoint of prioritizing candidate genes. So basically, the inputs of this formulation includes a query disease of interest. That's a specific type of disease. A set of candidate genes you would like to prioritize, and also a set of known associations between the query disease and the genes. The output would be a ranking list of the candidate genes. So in order to obtain such a list, people can score the candidate genes according to their biological relevance to the query disease, and then rank the candidate genes. Finally, they can further test the functions of those candidate genes, and with high ranks for their roles in the query disease. So most of the scoring functions so far are designed based on the so-called guilt by direct association principle, which assumes that a disease is caused by genes that have similar functions. Therefore, a gene is likely to be associated with a disease if the gene shares some common characteristic with genes that are already known to be associated with a disease, or we just simply say seed genes. So such kind of common characteristic can be some sequence features, gene expression patterns, functional annotations, and also widely used network-based features. For example, you can simply map all of the candidate genes you want to prioritize to a protein-protein interaction network, and then you can also map those seed genes to the same PPI network. Finally, you can calculate the distance from each of the candidate gene to the seed genes and use this as a score. Finally, you can rank those candidate genes according to their scores. So in this diagram, the protein-protein interaction network actually serves as a systematic yet simplified view of functional relations between all genes and their products. So in our work, we simply refer to such a protein-protein interaction network as a human interactome. But as you can imagine, such kind of methods which rely on seed genes have a limitation. So simply say, because the number of known seed genes are in general quite limited, the power of this method might be impaired. More importantly, actually for diseases whose genetic bases are completely unknown, which means that we don't know any seed genes for those diseases, we cannot apply this method. So in order to solve this problem, you may intuitively just borrow some seed genes of other diseases and use them to help the prioritization of candidate genes for the query disease of interest. Okay, so this is made possible by the introduction of a so-called human phenome. Actually, it's a pairwise similarity profile or known human diseases. And this profile is obtained by extracting records of disease phenotypes from the MIM database, mapping those records to the medical subject headings vocabularies mesh, and then calculate the distance between two, also the similarity between two diseases as the cosine of the angles between the corresponding vectors. So basically, we first represent a disease as a vector in the high-dimensional clinic space, and then calculate their similarities as the cosine of the angles between the corresponding vectors. And this phenome actually is represented as a huge matrix of containing pairwise similarity values for every two human diseases. So this phenome, together with interactome, as we just mentioned, and also some known associations between diseases and genes, from the so-called phenome-interactome network. And there have been a lot of methods depending on the phenome-interactome to prioritize candidate genes. So most of them are designed based on the so-called guilt by indirect association principle, which assumes that similar diseases are caused by genes that have similar functions. For example, in 2008, our group proposed a method called CIPHER, which uses a linear regression model to explain the similarity between every two diseases using the similarity, or say the network proximity of genes that are known to be associated with the disease. And in 2009, we further proposed a method called align-PI to align the phenome network with the interactome network. In 2010, there have been two methods proposed. One is called RWRH. Actually, it's a random walk model, which simulates a stationary distribution of a random walker staying on each of the candidate genes, given they start from the seed genes. Another is called the PRINCE. Actually, it uses a network propagation model to simulate how the disease status propagate in the phenome-interactome network. And in this year, we further proposed two methods. Actually, we extended the linear regression model and solve the linear regression model using a Bayesian approach, and then we apply this method to actually identify possible associations between protein domains and human complex diseases. Okay, but most of these methods, as I mentioned above, are based on probabilistic models, which are typically very computational intensive. So in this work, we propose the first combinatorial approach called MaxIF. Actually, its meaning is maximizing the information flow for prioritizing candidate genes. So recall what we have is a set of candidate genes that might be obtained from some linkage analysis or association studies. So what we want to have, the output would be a ranking list of this set of genes. So in order to obtain this list, we first construct a flow network. In computer science, people will say flow network from the phenome-interactome network, and then we look at how the flows can be pushed through each of the candidate genes. And we use this information as an association score for each of the candidates, and then finally we rank those candidate genes according to their scores. So this is the basic idea of our approach. So the first thing is we need to construct a so-called flow network from the phenome-interactome network. We do this as follows in 3 steps. So in the first step, what we did is very simple. We introduce a source node and a sink node. So for the source node, we further introduce a edge connecting it to the query disease of interest. So for each of the candidate genes, we introduce an edge connecting the candidate gene to the sink node. So this is the first step, very simple. So in the second step, we need to introduce the so-called width, or say the capacity for each of the edge in the flow network. So for the edge connecting the source node and the query disease, we simply assign the weight as positive infinite. The same thing, is done for the edges connecting each of the candidate gene and the sync node. So the weight will be positive infinite. Okay, so for each edge connecting two diseases, remember actually this kind of edge representing the pairwise similarity between two diseases. So for this kind of edge, what we did is we introduced a parameter called alpha, and we keep only edges whose similarity score which means the similarity between these two diseases should be greater than or equal to alpha. And for all other edges, we just discard. So which means we actually filter out those low similarities between diseases. We only keep, or say we only use this high similarity between those diseases. Okay, so for the protein-protein interaction network, or say the protein-protein interaction edge, what we did is we introduced a parameter called gamma, and then we assign this gamma to all the edges. So all the edges in the protein-protein interaction network have the same weight, gamma. Also for all the edges connecting the A disease and the gene, what we did is we introduced a parameter called beta, and we assign this beta to all such kind of edges. Okay, so by doing this, we will obtain a weighted network. So the third step is we need to assign the directions to those edges in order to obtain a directed network. So it's actually easy to understand. So for the edge connecting the source node and the query disease, what we did is we let the edge pointing from the source node to the disease of interest. Okay, so also for each of the edge connecting the one of the candidate gene and the sync node, what we did is we assign the direction as pointing from the candidate gene to the sync node. So for other three types of edges, we just treat them as bidirectional. Okay, so by performing these three steps, what we got is we obtain a so-called flow network from the phenome-interactome network. So with this flow network, what we can do is we can simply apply some efficient algorithm, such as push label algorithm or the binary blocking flow net algorithm to this flow network and obtain the maximum flow that can be pushed from the source node to the sync node. So with the values of those flows for and each of the edges being calculated, we can further then look at the net flow value that are pushed through each of the candidate genes and use this net flow value as the association score for the corresponding candidate gene, and then further to rank those candidate genes according to these net flow values. So noting in this process, those algorithms may require the so-called integer capacity for those edges. I'm sorry. So this can be easily done by you can multiply your weight assigned here with a large integer and round the resulting number to the nearest integer. Okay, so far so good. Well, here we already have this max-if method. So once you have a computational method, what you need to do is you need to first validate that your method is correct and efficient. So here we adopted two sets of cross validation experiment. So the first one is called the Lewin out cross validation, or simply you see the ROOCV. So the second one is called ab initio prediction. So for each one of the Lewin out cross validation, what we did is we select an association between a query disease and a gene. as from some database, and then we assume the association is unknown, and we prioritize the gene against a set of control genes. So in the initial prediction, what we did is we further remove all known associations between the query disease and the gene, because it is possible that the query disease is known to be associated with multiple genes, and the inclusion of such information will obviously ease the identification of novel genes. We further adopted two sets of control genes. The first set is we'll just select genes that are located in 10 megabase pairs upstream and downstream around the disease gene. We call this validation as validation for a linkage interval. Another is for random control, which means we just randomly select some genes as a control gene. Okay, so by performing either of these two validation experiments, what you can get would be a set of ranking lists. Okay, so for in each list, you will have a disease gene and some control genes, right? So this gene is marked as red, and the control genes are marked as green. So with this ranking list, you can simply calculate the mean ranks of these disease genes and obtain a criteria called mean rank ratio. Actually, the smaller the better. The second is you can calculate the fraction of disease genes which are ranked at the top of the ranking list and obtain a criteria called precision. The higher the better. Finally, what you can do is you can set up a threshold value, and you claim all genes ranked above this threshold as disease genes, or say positive, and you claim all genes ranked below this threshold as negative, or say non-disease genes. And you can further calculate the fraction of true disease genes that are claimed as positive, and you obtain the sensitivity, the so-called sensitivity. Similarly, you can obtain specificity, which is the fraction of non-disease genes ranked below this threshold. So by varying this threshold value, what you can get is a list of sensitivities and specificities, and you can then plot a ROC curve and further calculate the area under this curve as an AUC score. So we perform such kind of validation experiments with these two evaluation criteria to a data set which contains about 5,000 diseases, 9,000 genes, and about 3,000 associations between those diseases and genes. And we can see that the AUC curve is like this, and our method we can see that our method is effective because the AUC score you can reach more than 90%. So if you permute one of those networks, such as permute the phenome network, the interactome network, or say the associations between the phenome and the interactome, the AUC is only about 50%. Okay, so secondly, we actually checked the robustness of our method to the parameters involved, because actually we have 3 parameters involved in our method. So the method is, in order to check the robustness, what we did is we just vary the parameter values and see how the method performs with the change of this value. And what the result we obtain is that our method is quite robust to the parameters involved. So this is for the parameter alpha. You see all the AUC is above 94%. Also, we did this for the parameter beta and gamma, and we obtain similar results. Okay, so far so good. We have our method, the correctness, and also the effectiveness of our method validated. So in the next slide, a few slides, I would like to show 2 applications. we also compared our method with two existing methods, random walk and Prince, and we see our method is actually perform better than theirs. Okay, so I would like to show two applications. So the first one is the reverse prioritizing of candidate diseases. So we have shown that we can prioritize candidate genes, but some people might be interested in the reverse problem of identifying for a fixed query disease gene, the diseases with which the gene are most likely to be associated. Okay, so for this purpose, actually, you can intuitively just reverse the direction of reverse everything in our previous diagram. For example, the source node, the sink node, and also the direction. You just reverse them, and you can obtain another flow network. Then you can maximum the information, the flow in this network, and also obtain the scores to rank those diseases. So we also perform the leave-out cross-validation and the initial prediction and to check the performance of this diagram, this formulation. We see that our method is effective. So the second application is about the identification of driver genes in cancer studies. So suppose you have a number of copy number aberration regions, and you can obtain, or say, each of the region may contain some genes. So which one of these gene is the driver gene, and which is the disease are the passenger gene? That's a problem. So what we did is for each of the CNA region, you can extract all genes in the region as candidate genes, and you apply this MaxIF method to prioritize these candidates, and then predict the gene ranked at the top as the driver gene. So we did this for for 50 code number aberration regions obtained from 62 cultured melanomas, and we predicted 47 driver genes from a total of 400 candidate genes. So these 47 driver genes predicted driver genes. Some of them, such as ITF, this KLF6, and also some others are consistent with the literature, but some others are novel predictions. So here we further list the functions. And we also did some other analysis, such as we checked the modularity of the predicted driver genes, and we found that actually they tend to form some small connected components. And that's it. Okay, so the result, so this work presented is made possible by the support of the National Science Foundation of China and some other fundings from the Tsinghua University. I would like to also thank each of you for your kind attention. Thank you very much.